We can cast the second law of thermodynamics into a pure mathematical form that is called Clausius' theorem or Clausius inequality. First, we derive Clausius inequality for a heat engine exchanging heat with two thermal reservoirs, a hot source and a cold sink in a Carnot cycle represented with the closed curve A, B, C and D in the pressure-volume diagram. As the figure of the heat engine and the thermal reservoirs operating in the Carnot cycle shows, the engine absorbs the heat Q1 from the hot source at the temperature T1 in the step of isothermal expansion of the working substance along the curve between the points A and B in the pressure-volume diagram. By completing the cycle, the heat engine delivers the work W' given by the area of the closed shape A, B, C and D, while it rejects the heat Q2' to the cold sink at the temperature T2 in the step of isothermal compression along the curve between the points C and D. We saw that the thermal efficiency eta of a Carnot cycle defined by the ratio of the work W' done by the heat engine to the heat Q1 absorbed by the engine is equal to the ratio of the difference between the heat Q1 and the heat Q2' to the heat Q1 due to the law of conservation of the energy. Carnot's theorem states that this value obtained for the thermal efficiency eta is always less than or equal to the difference between the temperatures T1 and T2 of the hot source and the cold sink divided by the temperature T1. If the Carnot cycle is reversible, then the equality holds, whereas the efficiency is less than this ratio for an irreversible cycle, which can also be written as 1 minus the ratio of the temperature T2 to the temperature T1. Since the heat Q2' rejected to the cold reservoir is equal to minus the heat Q2 absorbed from it, the thermal efficiency eta can also be expressed as the ratio of the sum of the heat Q1 and the heat Q2 to the heat Q1, where both Q1 and Q2 denote the heat delivered to the engine from the thermal reservoirs. Obviously, a positive value of the heat Q2' rejected by the engine results in a negative value of the heat Q2 delivered to the engine. Then the left-hand side of the equation is given by 1 plus the ratio of Q2 to Q1, and this value is less than or equal to 1 minus over T2 to T1. As a result, we can write that the ratio of Q2 to Q1 is less than or equal to minus the ratio of T2 to T1. If we multiply this expression by Q1 and divide it by T2, we obtain another form of the expression stating that the ratio of the heat Q2 to the temperature T2 is less than or equal to minus the ratio of the heat Q1 to the temperature T1. In this expression, each ratio of the heat to the temperature characterizes the transport of energy in one step of the Carnot cycle, where the heat is exchanged between one of the thermal reservoirs and the heat engine in an isothermal process at the temperature of the thermal reservoir. Motivated by this fact, Clausius introduced the concept of reduced heat and defined it by the ratio of the heat absorbed from a heat bath in an isothermal process to the temperature of the heat bath. Then the ratios Q1 over T1 and Q2 over T2 are the reduced heat exchanged by the heat engine and the thermal reservoirs in the Carnot cycle, and Clausius inequality can be formulated as follows. The sum of the reduced heat in each isothermal step of the Carnot cycle cannot be greater than 0. That is the ratio of the heat Q1 absorbed from the thermal bath to the temperature T1 of the thermal bath, plus the ratio of the heat Q2 absorbed from the thermal bath to its temperature T2 of the thermal bath is less than or equal to 0. The sum of the reduced heat only vanishes if the Carnot cycle is reversible, otherwise this sum is less than 0. This result can be generalized to any cyclic process in thermodynamics in the following way. Let us consider a thermodynamic cycle represented by the closed curve calligraphic C in the pressure-volume diagram, where the arrow on the curve indicates the direction of the cycle. We also draw a Carnot cycle such that its states A and C are on the curve calligraphic C representing the thermodynamic cycle, where the heat is absorbed from two heat reservoirs at the temperatures Ti and Tj. As already seen, the steps of isothermal expansion and compression in the Carnot cycle are represented by the curves between the points A and B, and the points C and D along the isotherms, that is the red hyperbolas. The adiabatic processes in the cycle take place between the states B and C, and the states D and A along the adiabats represented by the yellow curves. Let delta Q star I and delta Q star J denote the heat absorbed from the thermal reservoirs at the temperatures Ti and Tj during the isothermal expansion and compression of the cycle. Now we consider another Carnot cycle represented by the closed curve connecting the points A', B', C' and D' with the isotherms at the temperatures Tk and Tl, where the states A' and D' are on the adiabat connecting the states B and C of the first Carnot cycle. Here the heat absorbed from the heat reservoirs at the temperatures Tk and Tl are denoted by delta Q star K and delta Q star L. We already derived Clausius inequality for Carnot cycles, and we can write that the ratio of the heat delta Q star I to the temperature Ti, plus the ratio of the heat delta Q star J to the temperature Tj must be less than or equal to 0 for the Carnot cycle between the states A, B, C and D. We have the same inequality for the second Carnot cycle as well, only the indices I and J must be replaced with the indices K and L. If we consider the combination of the Carnot cycle A, B, C and D, and the Carnot cycle A', B', C' and D', then we need to add the ratio of delta Q star K to Tk and the ratio of delta Q star L to TL to the left-hand side of the Clausius inequality. Since the two Carnot cycles have opposite orientations along the adiabat between the states B and D', their contributions cancel out each other along the curve between the points B and D' in the total work given by the integral along the closed curves of the cycles. As a result, we can replace the two Carnot cycles with one thermodynamic cycle connecting the states A and B, B and A' and B', B' and C', C' and D', D' and C, C and D, and finally D and A. This result indicates that an arbitrary thermodynamic cycle can be constructed from, or at least approximated with a series of Carnot cycle when we study the exchange of heat in that process. In order to proceed with such a construction or approximation, we have to examine the exchange of heat in both the thermodynamic cycle and its approximation with Carnot cycles. The pressure-volume diagram shows that the states A' and A are connected with two different paths. The path along the curve calligraphic C, and the paths connecting the states A and B, and the states B and A'. Here we reverse the orientation of the path between the states A and A' along the curve so that it could form a cycle with the paths connecting the states A, B, and A'. Since the thermodynamic process between the states B and A' is adiabatic, delta Q star I gives the total amount of heat exchanged in the process with the steps AB and BA'. However, the amount of heat is generally not equal to the magnitude of the heat delta Qi absorbed in the process represented by the curve C between the states A' and A. Similarly, the magnitude of the heat delta QL absorbed in the process along the curve calligraphic C between the states C and C' is generally different from the magnitude of the heat delta Q star L absorbed in the steps CD' and D'C'. Again, the path connecting the states C and D' is an adiabat where there is no exchange of heat. Now we can consider the closed path connecting the states A', and B as a mini-thermodynamic cycle. Similarly, the closed curve connecting the points C', C, and D' also represents a thermodynamic cycle. Then we can apply the first law of thermodynamics for these cycles, stating that the net heat absorbed in the mini-cycles must be equal to the work done in the cycles. The net heat absorbed in the first cycle is given by the difference between delta Q star I and delta Qi, which is equal to the work W' given by the green area of the plane figure defined by the points A', A, and B. The negative sign of the heat delta Qi indicates that the mini-cycle between the states A and A' and the thermodynamic cycle represented by the curve calligraphic C have opposite orientations. The same equation can also be written for the cycle C', C, D' with the index L instead of the index I and with the work W' given by the green area of the plane figure C, C', D'. Although this area is small, the plane figure A', B has a considerable size. Then the work W done in the first mini-cycle, that is the difference between the heat delta Q star I and the heat delta Qi, is not negligible. However, we can approximate the thermodynamic cycle represented by the curve calligraphic C with the series of Carnot cycles constructed from a dense network of isotherms and adiabats, where the total area of the cycles almost covers the area of the closed curve calligraphic C in the pressure-volume diagram. For the sake of brevity, we show only the sections of isotherms and adiabats forming the Carnot cycles. We also denote the intermediate states by capital letters only for two adjacent Carnot cycles. In the series of Carnot cycles, all the adjacent cycles share a path connecting two states, for example the states B and D', but they evolve along it in the opposite direction with respect to each other. As a result, the effects along the path cancel out for each adjacent pair of the Carnot cycles, and the closed curve calligraphic C can be replaced by the paths connected by the points A, B, A', B', ellipsis, C', D', C, D and so on. We can therefore approximate the thermodynamic cycle represented by the curve C with this series of Carnot cycles, where the n isotherms are used for their constructions, that is the heat is absorbed from n different thermal reservoirs. Here delta Q star 1, delta Q star 2, ellipsis, delta Q star n denote the heat absorbed from the heat reservoirs at the temperatures T1, T2, ellipsis Tn, and the Clausius inequality for the series of Carnot cycles in this construction tells us that the sum of the ratio of the absorbed heat delta Q star I to the temperature Ti from I equal to 1 to n is less than or equal to 0. In other words, the net reduced heat absorbed from all thermal reservoir in the sequence of the cycles is never positive. We see that the area of the plane figure A, B in the pressure volume diagram representing the work W' done in the mini-cycle A, B is small. Due to the first law, the difference between the heat delta Qi absorbed in the process evolving from the state A to the state A' along the curve calligraphic C and the heat delta Q star I absorbed in the process with the steps AB and AB' is also small. For each mini-cycle along the curve calligraphic C, we can compare these differences between the heat absorbed in a given section of the thermodynamic cycle and the heat absorbed in the processes along the paths constructed from the Carnot cycles. Then we find that these differences will be small provided the areas between the curve calligraphic C and these paths are also small. If we apply a more and more dense network of isotherms and adiabats, that is increase the number of Carnot cycles in the construction with the number of the thermal reservoirs such that n tends to infinity, the work W' given by these areas also tends to 0. As a result, the difference between delta Qi and delta Q star I goes to 0 for each adjacent pair of Carnot cycle where the index I runs from 1 to n. In other words, as the number n of the thermal reservoirs used in the construction approaches infinity, the processes approximating the thermodynamic cycle also approach the cycle and the heat delta Q star I tends to delta Qi. Then we conclude the following theorem. If a system absorbs the amounts of heat delta Q1, delta Q2, ellipsis, delta Qn from the thermal reservoirs at the temperatures T1, T2, ellipsis, Tn in a thermodynamic cycle, then the Clausius inequality holds, stating that the sum of delta Qi divided by Ti from I equals to 0 to n is less than or equal to 0 in the limiting case where n tends to infinity. Since the absorbed heat delta Qi approaches 0 as the number n of the thermal reservoirs goes to infinity, the infinite sum becomes a cyclic integral of 1 over the temperature T with respect to the heat Q, and the Clausius inequality states that the cyclic integral of the reduced heat absorbed in the thermodynamic system is never greater than 0. If the thermodynamic cycle is reversible, then the infinite sum or the cyclic integral vanishes, otherwise it is less than 0. There is a corollary of the Clausius inequality which is related to the thermal efficiency of any thermodynamic cycle or heat engine. Let us consider a thermodynamic cycle with n steps, that is where the working substance exchanges heat with 2 times n thermal reservoirs. Here we can see the pressure volume diagram of the cycle as shown in the proof of the Clausius inequality. We assume that the number n of the steps is very large, and the thermodynamic cycle is represented by the purple path along the isotherms and the adiabats. Then the curve calligraphic C represents the limit of the thermodynamic cycle in the diagram as the number n tends to infinity. Let delta Qi with the superscript 1 denote the heat absorbed from a hot source at the temperature Ti, and let delta Q'j with the superscript 2 denote the heat rejected to a cold sink at the temperature Tj. By definition, both delta Q super 1 sub I and delta Q prime super 2 sub j are positive quantities, and their sums give the total heat Q1 absorbed from all the hot sources and the total heat Q prime 2 discarded to all the cold sinks respectively. Then the Clausius inequality can be written as the sum of delta Q super 1 sub I divided by Ti from I equal to 1 to n, minus the sum of delta Q prime super 2 sub j divided by Tj from j equal to 1 to n is equal to or less than 0. Here the negative sign of the second sum in the left-hand side of the inequality indicates that the heat appearing in the numerator of the fraction is rejected to the cold sinks. Now we assume that the thermal reservoir at the temperature T1 is the hottest source used in the thermodynamic cycle, where the isotherm at the temperature T1 gives the path of a step with an isothermal expansion of the cycle between the states A'' and B'. Similarly, we assume that T2 is the temperature of the coldest sink used in the thermodynamic cycle, where the isotherm at the temperature T2 gives the path of a step with an isothermal compression of the cycle between the states C'' and D'. Since the temperature T1 is greater than the temperature Ti of any other hot source used in the cycle, by replacing Ti with T1 in the first sum in the left-hand side of the Clausius inequality, we obtain a sum which cannot be greater than the original one. Similarly, since the temperature T2 is less than the temperature of any other cold sink used in the cycle, the sum obtained after the replacement of Tj with T2 in the left-hand side of the inequality cannot be less than the original expression of the second sum. As a result, the modified form of the first sum, minus the modified form of the second sum cannot be greater than the original form of the first sum, minus the original form of the second sum, which is the left-hand side of the Clausius inequality. Then we obtain the following inequality. The ratio of the sum of delta Q super 1 sub I to T1, minus the ratio of the sum of delta Q super 2 sub J to T2 is less than or equal to 0. Here the sum in the numerator of the first fraction is equal to the total heat Q1 absorbed in the thermodynamic cycle, whereas the sum in the numerator of the second fraction gives the total heat Q'2 rejected in the cycle. Now we write the inequality stating that the heat Q1 times the ratio of the temperature T2 to the temperature T1 is less than or equal to the heat Q'2. The thermal efficiency eta of an arbitrary thermodynamic cycle or a heat engine is defined by the ratio of the work W' done in the cycle to the total amount of heat Q1 absorbed in the cycle. Here the work W' is given by the total area of the steps forming the whole cycle, and the first law of thermodynamics states that it is equal to the difference between the heat Q1 absorbed in the cycle and the heat Q'2 rejected in the cycle. By substituting the inequality obtained here into Q'2, we see that this fraction is less than or equal to 1 minus the ratio of T2 to T1, or the ratio of the difference between the temperature T1 of the hottest source and the temperature T2 of the coldest sink to the temperature T1. Then we have proven that the maximum of the thermal efficiency of a thermodynamic cycle or a heat engine equal to this ratio is a corollary of the Clausius inequality. Since eta is less than 1, we conclude that the heat cannot be completely converted into work by a heat engine, or more generally in a thermodynamic cycle.